What we've seen are actually what we call logic circuits. We note that we can summarize the first configuration by saying that switch 1 and switch 2 both have to be on in order for the light to be on. Otherwise, the light is off. Okay? And this leads us to what we call the logical AND operator. We'll talk more about that, but let's just put it in simple terms. Let's just say that switch 1 is P and switch 2 is Q. So we have a P switch, we have a Q switch. Okay? And we have here P and Q then. So what we say then is P and Q. So we have P and Q implies that the light is on. And we use this caret type symbol to indicate AND. So now we can list our rule for the first switch. Excuse me a minute. Okay, I'm going to back up just a little bit. We want to look at this table that describes the behavior of the two switches. Switch 1 will stand for P. P will stand for switch 1. Q will stand for switch 2. P and Q means two switches are both on. Okay, so is the switch on? Question mark. Well, we're going to answer the question for each of the switches as to whether it's on or off by true or false. True if it's on, false if it's off. So in the first case, the first switch was off, the second switch was off. So we say both the P question, is the first switch on, is false. The Q question, is the second switch on, is false. And similarly, P and Q. Now the answer over here means, is the light on? And right here, the question is the light on? And the answer is that statement is false. Let's try to say the light is on, it's false. Okay? Here, first switch is off, so the answer to the question, is the switch on, is no, or the assertion that the switch is on is false. The second switch, the Q switch, is on, so that's true. So the combination, is it on or off? Well, it's still off, because as we saw, having either switch off is sufficient to make the combination off. Okay, so now in the third case, here now the first switch is on, the second is off, and the light is still off. In the last case, the first switch is on, the second switch is on. Things are getting a little jumbled here. Not such a good idea. But in this case, the light is on. So this represents the behavior of the first system. Okay? Now, second system, same questions. So we have the same trues and falses since the first two lines of the table are set up just as they were here. So we have false, 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 true, true, false, true, true. Okay, so when we have the false, false, meaning that both switches are off, then the P or Q is false, meaning that the light is off. Okay, false, true, well, that turns the light on. An off and an on will turn the light on. An on and an off will turn the light on. And both switches being on will turn the light on. Okay, now the use of the word OR here is maybe a little different than the use you would think. Usually when people use OR, they're meaning either or, but not both. Okay, but the logical OR means this switch is on. If this switch is on, then it's on. If this switch is on, then it's on. And it doesn't matter if it's just one or both. So the logical OR just means they're not both false. Okay, if I say this or that, what I'm saying is my statement is true as long as both this and that are not both false. If at least one is true, it's true. If they're both true, it's true. Now, the way OR is often used is either but not both. Well, that logically is called our exclusive OR, XOR, exclusive OR, and it's indicated by this symbol. So let's just do a table using the P and Q. We don't have to talk about switch 1, switch 2. We just talk about what would happen if we were to wire a couple of switches or some combination of switches to achieve a logical OR, which means that the light is going to come on if this switch is on and this one is off. It's going to come on if this one is off and this one is on. But if they're both off or if they're both on, the light's going to stay off. Okay, so P and Q can take the states true or false. Each one can be true or false. So in keeping with the way we've listed these, which is kind of backwards from the way these things are usually listed, we'll deal with that a little bit later. Not difficult to make the transition. We say, okay, well, P and Q are both false. Then what can we say about P exclusive OR Q? What do you think? Pause until you have an opinion. Okay, well, they're both false. This is going to be false, meaning in the case of a switching network, the light is going to be off. Okay, now, if P is false and Q is true, then the P exclusive OR Q, what's it going to be? Think about it. It's going to be true because exclusive OR means either but not both. So here's either but not both. So the light is going to be on. That's going to be true. And of course, true, false satisfies the same condition. It's one but not both. So we're going to have a true here. But if both switches are on, well, it says either, not both. Exclusive OR. Both of them on, the light is not going to light. Now you can think about how you might achieve that, or even whether you can achieve that kind of a result with just some combination of switches. Now when I listed the switches, I chose to list off before on. Usually when you do a table for an AND, for an OR, for an exclusive OR, or for any other logical combination, we list trues before falses. Just like for flipping coins, we'll do heads before tails. There's no compelling reason why we have to do it that way. It's just the way people usually do it, and probably has something for the something to do with the fact that people kind of prefer true to false in general. Okay, so we can write these tables out. Remember, the AND means that they both have to be true, so the only way we can get a true is for both of these to be true. So we have a true here, where both P and Q are true, and then we have false in every other case. For the OR, it's true unless they're both false. So the only way you're going to get a false, the only way the light is not going to light in this case, is if both switches are off. So the only way you're going to get a false is here, otherwise it's true. Then here, the exclusive OR, well, we have it over here. The table's going to look exactly the same, but the true is going to give us false, so we're going to have that here. The false is going to give us false. And in either case where exactly one is true, we're going to get a true. So this is the usual listing of these logical combinations. And this one and this one, as we've seen, we can easily achieve with just 2 switches. Question is, can we achieve this with switches, 2 switches or more switches if necessary, or is it simply not possible to do this with switches?